The mainstream intuition in AI engineering dictates that assigning multiple agents to a task creates more checks, catches more mistakes, and guarantees higher reliability. Two recent research papers argue the opposite. Adding agents often fractures the entire system. The March 2026 data explores why a multi-stage agent architecture frequently underperforms a single centralized model whenever no genuinely new information enters the system. Welcome back to the Bearded AI Guide channel. Today, we are opening up the systems design sandbox with the human architect. We are dissecting two formal papers from March 2026 to identify the exact mechanisms by which our most popular multi-agent frameworks amplify, spread, and harden factual errors. This analysis examines multi-agent systems as directed dependency graphs, mapping how local mistakes propagate into systemic failure. The current industry standard is to design agent workflows like a corporate board meeting. Engineers deploy executor agents alongside designated reviewer or QA agents, passing the exact same prompt context back and forth. This diagram represents a standard sequence: a planner, an executor, and a reviewer. Builders assume these sequential reviewers will scrutinize outputs and catch factual errors the same way a human manager would. The first paper challenges this assumption. It models multi-agent frameworks not as rational corporate boards, but as formal directed dependency graphs. Within these graphs, small atomic hallucinations do not get checked out of existence. They are passed down the dependency chain, where they amplify into a false consensus. Paper A explains this amplification through network propagation and topology. If a project manager begins a task with a bad assumption, the downstream team doesn't correct it. They build their work on top of it. One early mistake triggers a cascading chain reaction. This is a star network configuration. The research tests several common topologies and proves that multi-agent systems process errors entirely differently based on this structural layout. When a falsehood is injected at a high-leverage hub node, like a central planning agent, the error grows along the principal eigenvector, instantly infecting the surrounding leaf nodes. The network structure dictates the failure rate. A local factual error injected at a hub transforms into a system-wide false consensus, reaching a near 100% infection rate in empirical tests. As the network structure distributes the error, a secondary mechanism locks it in: consensus inertia. Inserting a false claim early in a pipeline is computationally cheap. Correcting it late in the pipeline becomes incredibly expensive because intermediate code, tests, and plans have already been written based on the bad data. In this workflow diagram, the system accumulates what the paper calls polluted rounds. Downstream agents write evaluation criteria that are mathematically consistent with the upstream error. The mistake gets buried under layers of structural dependencies. This creates state reversal resistance. By the time the output reaches the designated reviewer agent, the artifact is internally logically consistent. The reviewer passes it, even though the core factual claim contradicts external ground truth. Without a dedicated message layer mechanism to explicitly roll back the system state, sequential review agents are just rubber stamping the initial hallucination. The second paper shifts from network propagation to formal decision limits, detailing the mathematical penalty of compression loss. Watch how this sharp wave pattern loses its defined peaks as it passes through sequential filters. If you put 5 people in a room and give them all the exact same photograph, passing notes about the image doesn't generate new visual details. It just initiates a lossy game of telephone. In multi-agent systems, this is known as a delegated decision network operating in a common evidence regime, meaning all agents share the same underlying prompt in context. This visualization shows a common evidence pipeline. Theorem 7 from the paper proves that without new exogenous signals, this multi-agent directed acyclic graph is decision-theoretically dominated by a centralized Bayes decision maker. The multi-agent architecture literally reduces to a lossy communication encoder. The drop in reliability is mathematically measured as expected posterior distortion. Every internal communication step you add over a shared prompt mathematically degrades the underlying information available for the final execution, which leaves a crucial engineering question. Under what exact mathematical conditions does a multi-agent system genuinely outperform a single LLM? Returning to our 5 people in a room, if they stop staring at the same photograph and each pull out a magnifying glass, a historical archive, or an independent sensor, the team easily beats the individual. Architecturally, the dominance theorem only holds for the common evidence regime. Here, 3 separate agent nodes bring distinct complementary exogenous signals, such as private databases, isolated RAG pipelines, or unique tool outputs. This shifts the information structure from a common evidence reduction to a non-trivial team decision problem. Multi-agent architecture is only a valid design choice when it serves as an engine for gathering genuinely distinct data, not as a redundant reviewer of identical shared data. To prevent you from paying API costs for mathematically lossy systems, the human architect synthesized these proofs into a practical 3-gate decision framework. This is the decision flowchart. Gate 1. Does the added agent bring new exogenous signals? If it is just transforming shared context, you must assume it operates as a lossy channel that distorts your data. Gate 2. Where does the agent sit in the dependency graph? Upstream hub components are disproportionately dangerous injection points. Unverified claims placed there will saturate the network. Gate 3. Can the system perform early, localized correction? Your architecture must include a message layer provenance firewall to track claim lineage and execute atomic rollbacks before polluted rounds accumulate. Add an agent to your system only if it brings decision-relevant information. Otherwise, you are actively paying to amplify errors and increase your correction costs. If you want to keep actual systems engineering in your feed, hit subscribe. Drop a comment below on which specific multi-agent framework you want us to deconstruct next, or if you've noticed these topology failures in your own deployment. Because, as we always say here, systems fail at the seams. The research suggests that reliability depends less on adding roles and more on how well the architecture manages the information bottleneck.